So I now want to talk a little bit about the process of fatigue. And we can study fatigue on many different size scales, and of course people do. Starting at the atomic scale and then moving up, of course, to full-size structures. I like to think about the atomic scale because that's certainly where it begins. So fatigue happens because of plastic deformation, and plastic deformation is on that scale. So a picture on the left-hand side is actually an image of atoms. So it's made with an atomic force microscope. Atomic force microscope measures the small changes in magnetic fields as you pass around atoms, and then you turn that into some images. I like this one because it makes the atomic structure look like little round balls. I always think of the atomic structure that way. And in fact, I think about it as an array of billiard balls. And then if I want to build up a three-dimensional structure, then I just think about taking racks of billiard balls and putting them one on top of another, and I end up with a three-dimensional structure. And that's a pretty good analogy. Right? I mean, I'm not bothered by the details, that's not a perfect analogy or so on, but it's good enough. And if you want to deform something, and I think about this analogy, then if I have a plane of atoms or billiard balls, and I have another plane that sits on top of it, then to deform this, the hardest thing you can do is to pull it apart in tension. And that's because these atoms are attracted to one another with the interatomic binding force. And that's a very, very large force. And it's nearly impossible to pull them apart. I mean, we think about that when we look at fracture tests and so on, and we always think about pulling it apart in tension, but that's not what's happening at all. Right? If you want to move it, there are much easier ways. And so I always like to use an even simpler analogy. And while this floor doesn't have a carpet on, think about that if this floor were covered by some carpet and I wanted to move the carpet, the hardest thing for me to do would be to fold up the carpet and then lift it up in the middle. And that's analogous to pulling this apart in tension. In fact, you all know if there were a carpet in this room and I wanted to move it, the easiest way for me to move that would be to grab on one end and slide it along the floor. And that's what happens to deformation. So deformation really happens because of shear, not because of tension. So the tension test is really a misnomer. The tension test is really doing shear testing, right? And you're shear testing along 45-degree planes, and you can imagine that is much easier to do it that way. And then in materials, there's an even easier way to do it. Just like there would be a very easy way for me to move the rug on the floor, in that if I wanted to move a rug that was on this floor, one of the ways I could move it with the least energy would be if I put a wrinkle in the rug and then just push the wrinkle across the room. And when I push this wrinkle across the room, the rug would be moved in that direction by a small amount. And then I'd come back here and I'd do it again and again and again and again and again, until finally I could have a very large movement of the rug on the floor. And that's really what happens in materials. And you can imagine that now in the atoms, that what I show here is an array where there's an atom in every place. But imagine what would happen if there were a missing row of these atoms. And if there were a missing row of these atoms, then if I wanted to move something into this missing row, I could move the row behind it into here. That would leave this row missing, this one in, this one missing, and so on, one row of atoms at a time. And that's really what happens. Right, those missing rows are called dislocations. Here's an image of those dislocations in an electron microscope. Right? But these things all move by shear. They don't move by tension at all. So I've never understood why, if the physics has to do with shear stress, everybody uses tension stress in their analysis. Why would you use the wrong stress? Other than just like Goodman in 1890, well, it was easy. Pretty. Right? Tension is not the driving force. Right? Tension is the applied loads. Right? But the driving force for all material degradation, other than chemical, of course, is in the shear stresses. So there's a lot of study of fatigue at this size scale. Right? We won't study more about that, but I'll probably mention dislocations now and then. Next size scale, of course, is the crystal. That's the size scale that we see, and that's the size scale that you and Humphrey studied. And there's another whole group of people who study fatigue at the specimen size scale. So there's a size scale there. And of course, all the users want to use it at a size scale here. So I've talked enough about atoms and dislocations. I want to talk about what happens on the crystal level, because what happens on a crystal level is very important that you model the correct physics here. Because the physics of fatigue is complicated, and there's lots of different physics, and we try to make a model that captures the right physics, or the essential physics, but not all of it. If we ever try to build a model that would capture all of the physics, we'd never get here. Can you imagine telling the designer of the engine for this structure what the dislocations are in it, or what the atoms are in it, right? They just wouldn't use it. By the way, you recognize that structure as the space shuttle. I always like to ask a little question about the space shuttle and its power. So if I bought a new Ferrari, I'd like to have a new Ferrari, right? $400,000 or euros, right? At that money, it doesn't matter. 1-to-1 dollars to euros. It's not dollars okay right now, right? How many horsepower in a Ferrari?
400.
500. Huh? Pretty nice. Pretty good. I don't drive a Ferrari. I drive a classic American pickup truck, built in 1988. It's a wonderful vehicle. It's big. It's heavy. When I pull up next to somebody at the traffic lights in this big, heavy, old truck, they always move out of the way for me. It's no problem. It's no problem. Anyway, so here's the horsepower of my new Ferrari. Red. Does it come in any other color?
No.
No. Red. Okay,
Red.
good.
Must be red.
Good. What's yellow? The Lamborghini? There's a yellow one. Something.
Yeah.
Okay, fine. You can see how knowledgeable I am in a really good car. Unfortunately, my salary does not allow me to do other than to dream about these cars, just like you. Okay. How about the power of the engine that drives the biggest ship? Any ideas?
Hundreds of
The
thousands.
biggest one. Huh?
Hundreds of thousands.
Yeah, actually that's right. How about the power of the space shuttle? While you think, I will start writing. $18 million. Yes. Think how many Ferraris that would be. Probably the cost is the same. Probably the cost is the same. Amazing. So this structure burned. Yeah. Five. 200,000 liters of liquid hydrogen in 10 minutes. This is what's burned in that structure. Amazing structure. Amazing, amazing structure. But you know, if I was interested in fatigue and designing that, and there are serious fatigue problems in that, in the motors, in the pumps that pump this around, right? I'll show you more about that in a minute. I could never study fatigue at this scale and design that. Right? So we build models here, and we try to understand what is the right physics here to build the right model. So I will take a few minutes and talk about the physics of fatigue on that size scale. And so this is what I think of the fatigue process. Right? Cracks have to start if they're not already there. Then to get a failure, you need small crack growth in an elastic plastic stress field. If the stress fields are all elastic, even around the cracks, you don't have fatigue problems. There's not enough driving force. And then, when the crack gets bigger, you have macroscopic crack growth in a nominally elastic stress field, and then finally it breaks. Right? So, depending on where most of the life is spent, people try to model one or the other aspects of the fatigue process. So let's start at the beginning. So I showed you these pictures a little earlier, and now I want to talk about them. And so, like all professors, I want to make a simplified model. So there is my simplified model of the individual grains, all perfectly shaped and so on. And let's think about that I load this, and I'm going to load this in this direction. So I'm just going to pull this in tension and push it in compression. So we already talked earlier today that that's a non-proportional loading case, right? Because the principal stress directions change, right? But we recognize it as the simplest uniaxial load case. And if I looked at the picture, I might see something like this. And so I drew deliberately, I put all of these at some angle because the process is driven by shear, not tension. Shear, not tension. All plastic deformation is driven by shear. And what you notice is some of the crystals have these shear bands, which will eventually become cracks, and some do not. And this is why I spent a minute talking about pushing the rug across the floor. In that during solidification, every one of these crystals will solidify with some random orientation of planes. And if I think about the orientation and I wanted to form something easily in shear, then there's a preferred direction for which it's easy to shear and another direction for which it is not. And so if I looked at these grains, maybe this crystal is oriented such that the preferred shear direction is like this. What's the shear stress on this plane when I load this in tension? So I'm loaded in tension. What's the shear stress on this plane? 0. Yeah, sure. More simple. Right there, 0. I know you remember these things, but it's in the middle of the afternoon, so you want your nap. It's okay, I'll have to be a little bit more entertaining in the middle of the afternoon. I know that. Okay, 0. So, nothing happens here. And so, first of all, we see that the idea of fatigue has to be a statistical process, doesn't it? What are the chances that the applied loads can activate different planes in a material? And when those line up with one another, then you can form fatigue cracks. Okay. Other things to note. If we look over here we can see a particular grain, and we see these bands that form here, but they are contained inside of this grain. That is, they don't go outside of it. If they don't turn into a crack that grows, are they detrimental? No, who cares if they're there, right? It's a natural consequence of the material. So in order to get a failure, two things have to happen. First of all, I somehow have to nucleate a crack in one grain. And, like this one in the middle, then this crack or slip band that nucleates here must be able to go into the neighboring grain. And the neighboring grain must also be favorably oriented or almost favorably oriented as well. So to get a fatigue crack is not so easy. It has to have, the applied stresses have to line up to activate slip systems in a grain, and it then has to propagate that into the next grain. And this is exactly what Ewing and Humphrey found more than 100 years ago. Now, as I tell you this story, then you can see immediately it means that fatigue is a statistical process. We will never get rid of the scatter in fatigue. Because if I test two specimens, the orientation of all the grains, size of all these will not be the same. So it's impossible to find on a materials level a homogeneous isotropic material. It's just impossible. Right? Just impossible. It's not unusual to find fatigue lives that differ by factors of 2 or 4 or 5 or something like that easily, simply because of the statistics. Now, the picture I show you is what would happen if I tested at a very high stress level. If I tested at a low stress level near the fatigue limit, then maybe I would find one of these slip bands in 10,000 grains or one in 100,000 grains. So it's a very rare event, a very rare event. And it's that rare event ideas that lead to the scattering and fatigue. But again, this is all driven by the shear stresses, not by the tension stresses. So I'd like to show you these bands are real. And these are slip bands that are in copper. By the way, the space shuttle is made from copper, the main engine. Amazing structure, right? Well, I already told you the horsepower of the space shuttle main engine. So here's how the space shuttle main engine works, right? So there's a big funnel shape in the back, and that's copper. And it's essentially a copper radiator with lots of little tubes, passageways. And in this passageway, at the top, they put liquid oxygen to keep it cold. And they pass the liquid hydrogen in here to keep it cold so that they can burn it here. So if ever this fails, then the liquid oxygen and liquid hydrogen are pumped directly into here, and of course it all explodes. And that's how they get the tremendous power. The mechanical parts that have fatigue in the Space Shuttle main engine are thermal problems because of the temperatures, and also the pumps to pump this. Pump all of the hundreds of thousands of liquid oxygen and hydrogen from these big tanks into this engine. So there's a lot of research on copper. By the way, it was supposed to have a life of 100 flights. It has a fatigue life, I think, of about 5. Just about 5. And every time they tried to improve the behavior of this, and so they said, oh, we need to make this stronger. And so they changed the alloy and they changed all of those things. What happened was it makes the thermal conductivity worse. And the problem is worse, but it's stronger. By the way, this operates at a temperature above the melting point of copper. But copper is such a good conductor, it can take the heat away from the surface before it melts. It's an amazing structure. I wouldn't want to ride in it. It doesn't appear to be so reliable. Now here's slip bands in copper, and this is what you see. So this started off with a polished surface, and it started off like this. And then you can see that we have all of these bands that form, and you can see that these are planar, and you can see, and this is just a magnified view of that you have a band that's formed here and a band that's formed here, and you can see in the picture, get a notion that material is coming out of the page here, and here you can see some holes that have been formed in the material. No problem. And this was Ewing and Humphrey's idea before they saw any of this, what happened. So here's the outside surface of the material, and this is one of those slip bands going into the material. And so this is a cross section. And of course I'm going to load this in tension, and when I load this in tension, then I'm going to shear on this plane and this one, and of course all of them. And when I load this in tension, then these dislocations, remember, are missing rows of atoms, and these missing rows move out of the structure, and you get a little offset that looks like that. By the way, to get a hole, instead of having a missing row of atoms, you can have an extra row of atoms to move holes, so it's no problem doing that. So this is what happens in tension. And then in compression, this does not reverse itself. You can think about if I had an extra plane of atoms that moved out of the crystal, once it's moved out of the crystal, it's gone. And so now when I deform this next time, it will deform in some region near the first one, but not exactly the same, and you're left with a little bit of material that comes out of the material. And you have all done this experiment, by the way. So you can think about taking a wire. If you bend a wire, you can't straighten it. Now, when you try to straighten a wire that you have bent, then it will bend alongside of where you first did it, and you'll end up with a wavy wire because you moved all those dissipations out of your wire when you did it. Anyway, so you repeat this process. And of course, this does not happen every time. And this is a rare event that happens. But after a while, you accumulate these, and you end up with this slip band that comes out, or one that goes in. The other thing to note about this is that this material in here, this material and this material is undeformed. So when you look at this from the material science viewpoint, there is always plastic deformation well below the strength of the material, well below the yield strength. So from the macroscopic perspective, you say everything is elastic. True. Not from the microscopic perspective. Because remember, in the macroscopic perspective, if I were to put a strain gauge on this, I would measure the average deformation over this entire length. But of course, the deformation is 0 here and very large here. And estimates here are that maybe the strains are 10 times what the average deformation is. So strains are very, very high in these low values. And you can see that these slip bands are real. Here's one that's actually in section. So this, of course, started off completely flat across the top, and you can see how this material has come out of the surface. And you can also see how a crack is formed. So there's one. Jobs over and comes down. One is forming there, and you can see one forming right here, and so on. So sooner or later, everything will form a crack. If we cycle it enough times, sooner or later we'll always get cracks. So lots of ways of doing it. That happened to be in copper. Here's what happens in aluminum. Again, you can get some idea of the grains that are there. You can see slip bands that form. So here's slip bands forming in this grain. There's some that form in that grain. Eventually, this will link up and lead to failure. All driven by shear. And I said that's not the only way to do it. You can also have things in the material, deliberate or otherwise, so you can have an inclusion. And in an inclusion, a couple of things can happen to nucleate cracks. One of them is that this can debond from the matrix. And the other thing that can happen is you can have this act as a stress concentrator and develop a crack that goes there. So you don't need slip bands and everything. Right? There's a good example of what happens in particle cracking. And you know, with the particle cracking, you're still driven by the shear stresses at the edge for the plastic deformation in the matrix to get this crack to grow. And it's the shear stresses that cause that, not the tension stresses. This is what happens in titanium. In titanium, you can have a couple of different nucleation mechanisms. Either you can have slip bands, right, or it can nucleate from a hard inclusion. Now, this is the problem I worry about when I fly. Yeah, I'm never worried about the airframe. So when I fly home later this week, I'm not worried about the wing coming off. I'm never worried about that. It's no problem. I'm not worrying about the top coming off the airplane. It's just no problem. Right? I'm worried about the engine. Yeah, I had a friend who worked at one of the engine companies, Pratt & Whitney, and says, "Oh yeah, I always like to fly on a 4-engine plane." Now I thought that's because he wanted to sell engines, right? Of course, if you work for the engine manufacturing company, and he said, "Oh no, I want as many engines as possible on the airplane I ride because I know one could explode. Yeah, and it's because of this hard alpha inclusion. This is a processing flaw. What are the chances of this processing flaw getting rolled out into the highest stressed area of a casting that they make the turbine disc from? And if that happens, it will fracture. And there are a few instances of that happening. Right? I don't know that I have the number correct, but I think the acceptable level is that that can happen once in 10 million flights. That translates into about once every 10 years, an engine will explode in flight.
When was the last time?
When was the last time?
Adjusted.
Oh, it's actually just a little bit more. United Flight 232 in, I'm gonna guess 1986. But we're overdue. Okay. We're overdue. I should be. So, yeah. 4-engine planes. What's the 4-engine Airbus? 320? No, that's the little one. 380 is too big. Yeah. 380. Yeah, you know, all the modern airplanes are only 2 engines now. I worry about that a lot. So I flew on a 767, an old one, so old one, probably 25 years old. That airplane, which is 25 years old, probably already has had 50 different engines on it because of this problem. Anyway, lots of ways of getting cracks. Lots of ways of getting them. There's the last one, and you get some idea. You get some idea of size. This is in a hard material that you make a bearing or a gear from, and it fails from the inclusions. Just as another aside, I went to a talk on bearing steels, and they were talking about the fatigue strength, and it was a Japanese bearing manufacturer, and he showed the progression of steel over the last 30 or 40 years, and he put up a slide, and so you can imagine that the first slide he put up, and he said, here's the inclusion. You can imagine it was about that size on the slide. And he said, here's what we sold in 1980, and he gave the fatigue limit. And then he said, here's what we sold in 1990, and in 1990, then he showed a slide that kind of looked like that. And he said, you know, there's been this tremendous progress, and he showed what the fatigue limit changed, and it went up a lot. And then he put the, here's what we sell today, and he put up a blank slide. Or what appeared to be a blank slide, and he said, look what happens. And so, you know, these problems all have to do with the size of the crack nucleator. The size of the crack nucleator controls what the fatigue light is. All right. Okay. So that's the basics of how fatigue starts and how it gets there. It really does happen at the microstructural level. I keep saying driven by shear stress. And this is the classic diagram, which is in machine design texts everywhere, except in the machine design text, they never put the data points on it. They just put the lines there, and of course we know, in general, as you increase the tension strength of the material, that you also increase the fatigue strength of the material, or the fatigue length of the material. But if you look at this, then you see that there's a wide variation in what the ratio is between tension strength. So at this particular tension strength, I could have a wide range of fatigue strength. And that's because of this driven by the microstructure. The difference is something with a very low fatigue strength here will have big things in the microstructure, maybe one of those hard alpha inclusions. Right? So its fatigue strength is very low, and the stuff that's up here is a very good microstructure. Right? Very small inclusions and very, very tiny sizes. All right. So let's just summarize these ideas about crack nucleation. So first of all, it's a really highly localized plastic deformation that causes fatigue. And by and large, it happens on the surface. Now, I need some special definitions of surface. I have no problems with the surface inside the material. Well, why is that? I just think about a bimaterial. So I think about a shaft which has been hardened only on the outside. There's one material on the outside and one material on the inside, and so I think about a surface between the two. So if you allow me to have that definition of surface, fatigue happens on the surface. Physics reason is the surface grains are always weaker. The internal grains inside of here, if this were or a metal are much stronger than the surface because the surface is unconstrained. I think that's the reason. And I already showed you about that it's really a stochastic or a statistical process which we can describe. When somebody shows me some data that doesn't have very much scatter in it, I don't believe it. I don't believe they really are in the lab doing these tests if they bring me something that doesn't have very much in it. Yeah. The corollary to that, all the industrial people, of course, want to know exactly what is the lifetime of something. Another amazing thing. I did a design review for a company, and they were trying to benchmark themselves against a Japanese company, and they showed me the output of the fatigue calculations from this Japanese company, and the output. I don't know the exact one, but this was the output. Cycles, and they believe that number. I know a few of you are chuckling, all of you who have ever been into the lab. Wait till I tell you what it was from. This was from the wiring harness. That's how many times you could open and close your door before one of the wires would fail. So think about the variability in opening and closing your door. Every time you open and close your door, the wire doesn't take the same shape, right? Every time you open and close it, it's going to have a little bit different curvature, and of course it's going to be different because the plastic on the outside is going to be more or less stiff depending on whether it's the summertime or whether it's the wintertime, and all that kind of stuff. But they believe this number out to these decimal places. You know? So yeah, I don't know. It happens. It happens. And then the most amazing thing, there was a young engineer there, and I just kept telling him all these problems. And his response to me with a straight face was, it's just no problem. If we need to model that, we can just model that in Abacus Explicit. Because, of course, F equals MA, we can do anything. And I thought, well, they never hired me back because they didn't like reality. Okay, so it is stochastic, right? It is stochastic. We believe these numbers. Let's see. Okay, we believe maybe the first number on a good day. Okay, fine. And it is surface, and I want to show you some pictures that's really true. So here's what you see on the surface of something that's been plastically deformed, and here you can see this crack. And if you look only at the surface, you say, how could this transmit any force? Right? This is so severely damaged that this must fall apart immediately, and that's not what happens. And if I make a cross section through here, right, this is what you see. So you do see a lot of surface damage, but I can't break it. So again, I go back to my bar. So when I see this bar, then I see a bar which is 100 millimeters long and 15 millimeters in diameter. All right? More or less. What's the biggest crack I can have in here before it breaks? So I test this. I know you're afraid to answer my questions, and I know why. Because if I ask the question, the obvious answer is probably not correct. Why are you laughing? Sometimes the obvious answer is correct. I told you I taught machine design last semester, and so I gave a graph of some data. Okay? And I asked a question about how long something would last. And you could look up the answer on the graph. That's all you had to do is look up the answer on the graph. And I got the usual response. 1/3 of the students in my class looked up the answer on the graph, wrote it down, and said, you said in class sometimes the obvious solution is correct. I'm hoping. Okay? 1/3. Right? I gave them credit, right? 1/3 of the class curve fit the graph, solved the equations, and got the answer, of course, that they could have looking it up on the graph. Okay, so they learned, right? And 1/3 of the class had no idea. So I thought it was a good exam question. Good exam question, okay? So I want to ask you again, you don't know which of the three is correct now. What is the good strategy? I have this bar, 100 millimeters long, 15 millimeters in diameter. What's the biggest crack I can have in this bar?
15 millimeters.
15. So I hear both 15 and 100.
But
Yeah.
depends on the.
Yeah, exactly. And that's why I asked this question, right? You are right. I could have a 100 millimeter crack this way, and the bar would be just fine, either in tension or twisted, right, or bending. To break this, right, I have to somehow grow the crack through the thickness. So I have to grow it into the depth. And you can see that even though I have all of this surface damage, right, very few of these cracks actually can grow into the depth. This is the important part, growing into the depth. It's the part I don't see. If this were cracked and had the 100 millimeter crack along its length, I'd say that's really big, but that's unimportant. What's important is how deep does it go in. And it could grow 15 millimeters deep. And it doesn't matter the surface length. As soon as it gets 15 millimeters deep, this will grow. So let's look at that. So there are my pictures, so there are the grains. I want you to notice now that the grains are more irregularly shaped, like this. I got better at drawing the picture. Yeah, that's unfortunately, I was home. I was very sick for a while, and I had nothing to do other than stay home for 6 months and bother my wife and children. And so I learned to do almost everything in PowerPoint. So I learned how to make a PowerPoint and take apart PowerPoint objects and just do all that things to keep myself busy. And so that's why I have all of these slides. So I start making them and doing it, and so you can see I have more realistic grains and so on. And so now if we look at what happens, then cracks do nucleate more or less in shear, and after they go through a few microstructure units, then these always turn and they grow perpendicular to the applied loads. And so the reason that you use the tension stress when you look at fatigue is because that's what you see. You don't see this part where maybe all the life is consumed, where it's growing in shear. What you see is this part, right, the bigger cracks. And the bigger cracks always grow perpendicular to the applied tension. If I look very closely with a microscope, then they grow back and forth in shear. Because again, all plastic deformation is caused by shear. But macroscopically, they grow in tension. And this is a big problem now in fatigue. What stress system do I want? Do I want this one, things driven by the shear stress? Or do I want this one, things driven by the tension stress? Because the material will choose where it's going to spend the lifetime. The material will choose, and we'll talk about that. Just to show you that that's real, there you can see a crack which is shearing back and forth. Okay. Now I want to talk a little bit about what happens in structures. And to do that, I want to give you some idea about the size scale. So think about this as a plate, and that this plate has a cutout in it, and so it will be of this shape. And so I put a notch in the edge of this plate, and just to get some idea of size. And so if I ask, what is the volume of material that has high stresses in it? Then the volume of material that has high stresses in it will be on the order of the size of this notch, in this case D, and maybe 1 or 2 times D. And so I just draw that something like this. And so all these stresses will be very high in this region. And then if you have a fatigue problem, then around the stress concentrators, then you can also have some plasticity which is being driven by the stress concentrator. And that will happen in all structures. And then a tiny little crack will nucleate. And when this tiny little crack nucleates, then of course there will be a plastic field associated with the crack itself, and I draw that as this little black area. And what you see in this picture is that the plasticity driving the problem comes not from the crack, but comes from the geometry, the geometrical notch, and of course the nominal stress. And this is always the second stage of fatigue. The second stage of fatigue is I nucleated a crack and it's now going to grow in some plastic field. So let's look at how that happens. So this is a nickel-based superalloy. This is one of the alloys that they make these turbine discs from the engine. I was very fortunate as a young faculty member in that one of the other graduate students went to work for one of the jet engine companies, and they had a problem, and so he funded me to do some work in multi-axial fatigue, and in fact that's how I started doing this. And then he changed companies, and he funded me again, but so did the first company. So I now had two sources of funding to work on multi-axial fatigue. That did a good job, I guess. And then the best thing ever happened. After 10 years, he went to a third company. Yeah, all three of the American jet engine companies I had research contracts with from my friend who moved from company to company to company. And so I had lots of research money, and that's actually how I really did it. So I got a very nice laboratory and lots of graduate students and so on. So I know a lot about studying. This material. Okay. But from some time ago, very strangely, I was hired last year because of all of this work by actually Boeing in this case for the space station. So now that the space shuttle does not fly to the space station, they need to ship nitrogen to the space station. And they do that in a cylindrical tank. And this cylindrical tank has an Inconel liner on the inside so that the gas doesn't leak out. And then, of course, it's wrapped in composites and so on. And they had a fatigue problem. And they looked in the literature and thought I must be an expert because 20 years ago I published all of these papers funded by my friend 3 times. So, sometimes you get lucky. So I hope all of you get lucky when you go to work and, make friends. Make friends. It's easier to get research contracts with somebody you know. Anyway, what I learned through all of this is fatigue is pretty complicated. So let's just look at the beginning. So at the beginning you see this stuff. Of course, tension is loaded in this direction. You get some idea about size. So that's 100 microns. And smaller and then shear. And then as things progress, it's pretty complicated. Really, so you get that shear, and here's some stuff not yet linked up, and there's some stuff over here, and you can see with time, there's where it originally started, and this is growing in shear, and then out like that. And by the time the crack gets to be a millimeter or so, this is what it actually looks like. And that's what every real crack I see looks like in the lab. So if you wanted to analyze that, how would you do that? So of course you say, well, it's a crack, and I learned all this really good fracture mechanics from really famous professors, and I listened carefully, and I did all the homework problems and so on. And then you say, fine, I just know how to do that. And how do you do that? Well, I'll just need the stress intensity factor. That's pretty easy. It's mode 1. Let's see, mode 1, that's a crack that looks like that. I have never ever seen a flat mode 1 crack, ever. Unless I stand back here and look down at the end of the hall, then I probably wouldn't see it very well. So if I step back and back and back, maybe I'd see a mode 1 crack. But that's what real ones really look like. Okay? There's something pretty complicated as this is growing. By the way, you can see the progression of the growth of this crack, and then when the crack gets to this length, you see all of this damage out here and so on. That's what Ewing and Humphrey talked about in 1900, about once a major crack gets started, the damage is confined to the neighborhood of the crack tip. and the damage is confined to the neighborhood of the crack tip, because when these cracks are growing in plastic fields, here and here and here, this process is driven by the macroscopic plasticity around the knot. Right? Now, this crack has gotten big enough that the crack plasticity that's driving the problem comes from the crack. It comes from the crack tip plasticity. So already now, I've talked about 3 different physics I might model. So I might model the nucleation physics, right? All this shear back and forth, fine. I might try to model this stuff as this stuff links up and grows in a plastic field. Or I might try to model this stuff where the plasticity that comes from this is driven by the crack tip. How could a single fatigue model ever work? When I just showed you easily now 3 different sets of physics. Right? I can find a model that works really, really well in any of these 3 regimes. Right? But I can't find a universal model that works. I think that's impossible. Unless you have a model now that somehow knows to transition from maybe some slip band stuff to get to here, then knows about interacting with some other cracks in front, right? Maybe knows to link up and then grow. So it's a really complicated process. And that's why, even though I said earlier, we pretty much understood the physics of fatigue in 1900. Even today, nobody can model that. Nobody can model that complexity in the lower left. I can model any part of it, but nobody can model it. So that's why we still have problems in fatigue. By the way, if you look at what happens, the numbers on the top of these, the letters represent different loading paths. We'll revisit this slide a little bit later. The top numbers are stresses. And what you see is that if you think about it, you look at the lifetime along this axis, almost all of the lifetime is taken up, and these cracks are very, very small. Very small. And once the cracks get to be a millimeter or so, then they grow very quickly to failure. And that's what always happens whenever you look at something on the size scale of this for the test vessel. So almost all of the lifetime is taken up into formed cracks, which are on the order of 1 millimeter or thereabouts. So this is some very nice Japanese work. This is in aluminum. And of course, there's a particle in aluminum that nucleates the crack. And after the test was finished, then they etched this to reveal all the grains. And this is a drawing of all of the grains that are here. And during the test, then they carefully took replicas of the surface to monitor all of the crack lengths so you can get the crack growth rates. And here are the crack growth rates. And this is what 2 orders of magnitude difference in the crack growth rate. So of course the crack starts here from this inclusion, and what you'll see is that it grows, and if you look at this, as this crack approaches this grain boundary, you can see that it slows down for a while, and then it can go through this grain boundary and through this little grain, and now there's a little particle here, and you can see it slows down again, and tries to go through there, and then this crack grows and grows through some grains and slows down again as it goes through these barriers and so on. And we can make the same picture across here. Of course, this crack is growing and tries to hit this little inclusion. When it does that, it slows down for a little while and tries to grow around it. So here's even more complexity in the real fatigue process. But the other thing to notice from it, yes, there is a lot of complexity in this process, but by the time you get a size bigger than the microstructure, then the crack grows in a slow, stable, predictable rate. Right? And that's the region dominated by this crack plasticity. Right? The crack is big enough that it can grow on its own. But that's not always where all the lifetime is. And all the lifetime is when it's small. Right? So it's easy to analyze out here. Right? Easy to build models for what happens out here. Because now we are independent of the microstructure. Right? When we're out here, right, the microstructure really does look homogeneous and isotropic and all those things we assume. But not when the cracks are small. So when you are less than maybe 10 grain sizes of the material, then you'll have a lot of variability in the growth rate as these microcracks interact with the microstructure. So let me just summarize what happens in bigger cracks. So in bigger cracks, then locally, they shear back and forth like this. That happens locally, but macroscopically, these bigger cracks always will grow perpendicular to the maximum tension and stress. And as I showed you in the picture, the plasticity coming from the crack now is much bigger than the microstructure. So when this is much bigger than the microstructure, then this crack can easily move through it. You can just imagine if I have this drawn to scale, nothing about this grain is going to prevent this crack from tearing through it. But when this crack, microcrack, might be on the same order as this grain, then the size, shape, and inclusions will have a very big effect. So microstructure is so insensitive that, of course, you recognize this picture, growth rate on one axis, stress intensity on the other axis, that within classes of material, the crack growth rate is more or less constant. All the steels have a crack growth rate which are here. Cracks in aluminum grow 10 times faster, all else being equal. If you want to show aluminum as a better material, then you have to normalize this by either the weight or the modulus, and then it makes aluminum and steel look comparable. But in terms of absolute growth rate, things grow 10 times faster in aluminum than in steel. By the way, that's a big problem for the auto companies. You can't substitute aluminum for a steel design. That could be a disaster. It could be a disaster.